All right. Okay. Day 10, stability. Let's talk about stability first in terms of the system behavior. And I think this is kind of what's a little bit more natural for where you're at. We've already talked about stability a couple of times. What do I mean when I say that a system is unstable? What kind of behavior does it show?
Oscillates until infinity.
Yeah, so we have unbounded growing oscillations. Now, it doesn't have to be oscillating. It could actually grow in an unbounded way without oscillating too, right? So remember we showed in first order systems, if we have a positive real pole, it shoots off into infinity, but it doesn't oscillate, right? So we're going to give this definition of like oscillating in an unbounded fashion a little bit more rigorous definition here. So let's start out by defining what it means to be stable, and I'll try to do that without my eraser. There we go. Stable. And under this set of definitions is what we call the bounded input, bounded output definition. So a system, yep, BIBO, which is kind of funny because my daughter has a little book that's like these little elephants talking about their belly buttons, and the baby hippo says BIBO. So we're not talking about belly buttons here. We're talking about bounded input, bounded output.
You started for me.
I just did, yeah. Thank you. A system. Yeah, so here we are talking about belly buttons, and I will be posting this publicly to YouTube. A system is stable if every bounded input yields a bounded output. Okay, so if you give the system an input that does not blast off into infinity in either direction, you should receive an output that also does not blast off into infinity in either direction. Okay, so then that means that being unstable is if any bounded input yields an unbounded output. And we talked about an example of this. Does anyone remember the example here? One example of giving something a bounded input and receiving a non-bounded output?
The hanging pendulum.
Yeah, I was talking about my daughter swinging. So when she swings on a swing set, there is damping. But if you were to model the swing set without damping and you forced it at the same frequency as the natural frequency, so your input is just this nice, it doesn't blast off into infinity ever, but the swing is going to go, whoa, if we match the resonant frequency of the swing. Okay, so the input here is bounded, and the output here is unbounded. It grows off into infinity. Erase, 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 erase. There we go. Okay. All right. We also have a term called marginal stability. I think this one is kind of funny because I feel like it describes human beings. A system is marginally stable if the system is stable for some bounded inputs, but unstable for others. You gotta crash out every once in a while, right? Okay, if the system is stable for some bounded inputs, but unstable for others. Okay. I'm going to call these the bounded input, bounded output definitions. And these are all well and good. They give us in kind of intuitive understanding. If we see a system behaving in some way, in some unbounded fashion, we can say, that system is unstable. But ideally, we would prefer to be able to predict if a system is going to be unstable before it behaves in an unstable fashion, right? So what usually happens if something is becoming unstable? Is it usually good for your hardware? No. Yeah, most hardware does not appreciate being oscillated in an unbounded fashion. At some point, parts start flying off, motors fry, and things don't go so happy. So ideally, we would like to predict that a system is going to behave in an unbounded or unstable fashion. And so here we have a separate set of definitions that will help us to determine ahead of time if the system that we are looking at is going to be stable or unstable. And specifically, we're going to talk about stability in terms of the transfer function first, and then later towards the end of class, we're going to talk about stability in terms of the state space form. So when I talk about transfer functions, what domain are we in? Frequency domain. And I talk about state space form, what domain are we in? Time domain. Okay, good. All right, we'll cover both. All right, in terms of transfer functions, to be stable, stable systems have closed loop transfer functions What part of the transfer function do you think is going to help us figure out what's going on? Poles. Yeah, it's always been the poles before now. So the poles are what tell us a lot about the behavior. Okay, functions with poles only in the left half S-plane. In the left half S-plane. If we remember, the S-plane is this plane where we have the real is the x-axis, imaginary part is the y-axis. And if our poles are to the left here, we are stable. Homework right here. Yep. Okay. So another way to say this is that all of the poles, all poles have negative real parts. Zoom out a little bit. Okay. Unstable is going to be the opposite, right? If we have poles with positive real parts, the system will be unstable. So it turns out there are actually two different conditions that can cause us to be unstable. One is to have a pole in the right half plane, and the other is to have a repeated pole that is perfectly on the imaginary axis. So a pole of multiplicity greater than 1 on the imaginary axis. So just a quick reminder of multiplicity. The multiplicity of a pole refers to how many times it appears. So if I'm able to factor my characteristic polynomial, let's say we had s minus 4, s minus 4, s minus 4. The pole 4 would have multiplicity 3 because it appears 3 times. It's exactly 3 separate times. Okay, so let's look at what I mean here on the plane. On the S-plane, I am unstable. We'll color that red because instability is bad. If I am to the right, or if I appear twice in the same spot on the imaginary axis. Whoops, meant to make that smaller. All right. Yes, Jerry.
So we have greater than 1. If it's only once, is it neutrally stable?
Yes. Yep. It'll oscillate with oscillations that never damp out, but they also will not grow to infinity. Yep. Okay, marginal stability has systems that have, sorry, I'll try to keep that up there. Systems that have closed loop transfer functions with poles in the left half plane and or purely imaginary axis poles with multiplicity equal to 1. Okay, if we draw this on our S-plane, these poles would look something like this. On that plane. They are not repeated though. All right, let's do an example. Let's do an example with this system here. All right, I've got a simple feedback loop with just a feed forward G transfer function in the top. And I want to figure out, is this thing stable, unstable, or marginally stable? All right, so what do you think the first thing we need to do is?
Find the transfer function.
Yes, we need to find the closed loop transfer function, right? So this is a transfer function, but it's only the transfer function of the system within the loop, right? We now know, after doing block diagram reduction last class, we know how to reduce a feedback loop into its own individual transfer function. And so that equation is right here. I was nice enough to provide it. All right, so if we pretend that this block up here is G, and we pretend we have an H equal to 1 or a unity, because there's no system on that feedback loop, then our closed loop transfer function should look something like this. 3 over s squared plus 3s plus 2 over 1 plus 3 over s squared plus 3s plus 2. Okay, that looks pretty nasty. What do you think we could do to this thing to make it look a little bit more like a polynomial over a polynomial?
Multiply the top and bottom by s squared plus 3s plus 2.
Beautiful, yeah. So we can multiply the top and the bottom by this nasty term here that was originally in the denominator of the transfer function. Okay, so if I do that, I multiply by s squared plus 3s plus 2 over s squared plus 3s plus 2. I should get 3 over s squared plus 3s plus 2 plus 3. So we'll just call that plus 5. Okay, we got our closed loop transfer function. Great, what's next? We need to find the poles. How do I find the poles? Right? Okay, so I need to find the s values that make the denominator 0. And I can do that. I have a nice quadratic function here, so I can use the quadratic equation to find those poles. Okay, so we'll say s equals negative b plus or minus square root b squared minus 4ac all over 2a. All right, if we reduce this down, we should get minus 3 halves plus or minus 9 minus, or square root of 9 minus 20 all over 2. And this boils down to minus 3 halves plus or minus square root 11 over 2 times I. I just brought out that negative that was under the root. Great, let's see what that looks like on the S-plane. The real part of this, the coefficient or the term that doesn't have an I attached to it, is it positive or negative? Negative, yeah, I'm over here at minus 3 halves. And then I have a plus or minus square root 11 over 2. I'm not going to worry about exactly what that value is, but this is roughly what my poles would look like. And I know that if all of my poles are in the what half plane? It is stable. Very good. So are the poles in the left half plane that I'm abbreviating LHP as left half plane? I can say yes, ma'am, or yes, sir. Both poles have negative real parts. This thing is stable. Both poles have negative real parts. Stable. Beautiful. Any questions with this example? Fairly simple so far. What could possibly go wrong? Martin?
So were you reducing it to get the full transfer function? Is G not the full transfer function?
No, G is just this feed forward system. And when we do the closed loop transfer function, like this equation right here, it's built for a transfer function it's built for a feedback loop that has a transfer function in the feed forward rung and a transfer function in the feedback rung. Yep.
So we're reducing them into one transfer function?
Yes.
To see if the whole system is stable?
Correct. Yep. Very good. All right, let's do a second example. This should look extremely familiar. What is the only difference between this one and the last one we did? Look at that transfer function. What's the only? I just bumped up the order of this problem by 1. I just multiplied the denominator by s. That's it. Should be just as easy, right? Let's try it. So I still need to find that closed loop transfer function. Let's do that. First is g, so 3 over s cubed plus 3s squared plus 2s, all over 1 plus g times h, so 3 over s cubed plus 3s squared plus 2s. Going to do our same trick as always, multiply by that ugly denominator on top and on bottom. I'm kind of rude to denominators, aren't I? We should get 3 over s cubed plus 3s squared plus 2s plus 3. Okay. How do I find my poles? Martin?
Can you, never mind.
Yeah, Adney?
We tell people to find the roots of that.
In all actuality, I would say that the answer is probably something very similar to that. But we're engineers, so we don't use Google for finding roots. We use MATLAB for finding roots. Yes, absolutely. So that sets up my story for today. So the problem, as soon as we move above a second order system, so our s in the denominator has anything higher than a squared, we get in trouble because it's very hard to factor those higher degree polynomials, higher power polynomials, right? So the problem was, way back in the day when people were first working on these early control systems, is they would run into a very high degree polynomial and get stuck. And they say, okay, I can't factor that, so how the heck am I supposed to find my poles? In comes what we call the Routh-Hurwitz criterion that we're going to learn about today. But of course, that criterion was established in roughly the year 1876. Was Google or MATLAB available in 1876? No, in fact, the first commercially available personal computers didn't come around until about 100 years later, in about the 1970s. Okay, so what we're going to learn about today is a way to determine the stability of a system without actually computing the poles themselves. So without finding the roots of these high order polynomials. And I will give them their due. Way back in the day, they came up with some very kooky, interesting ways of figuring out how to find this. And I, being completely honest, I could not tell you the proof of why this works. But it does. Okay, and we do not have to compute the actual pole itself. All right, so my question here is, how do I factor s cubed plus 3s squared plus 2s plus 3? There are actually a couple of ways that you can look directly at the polynomial and determine if it is unstable. These are only to determine if it is, in fact, unstable. And these are the kind of first go-tos. So if all of the coefficients of this denominator polynomial are not the same, it is unstable.
have to be a cubic, quadratic, linear term?
That's a very, very great point. The next criterion is if there are any powers of S that are missing from the polynomial. It's either unstable or at very best it's marginally stable. Okay, so if I, for instance, if I threw away this term and I said I have S cubed plus 2S plus 3, the best that I can hope for is that this thing is marginally stable, but it may be unstable. Okay, if any powers of S are missing from this polynomial, it is either unstable or marginally stable. Big caveat here, though. Neither of these statements help me to certify stability. I can certify that something is unstable based on these criterion, but I can't certify that it is stable. So, however, even if neither of these cases holds, I can still be unstable.
Is that first condition about the signs of the coefficients, or is it the coefficients of the denominator?
Yes, signs. It's supposed to say signs, sorry. If all of the coefficients of this denominator are not the same sign. Yep, thank you so much. So if, for instance, if I have like a minus S cubed plus 3S squared plus 2S plus 3, then I know it's unstable. Yep. Okay. So in all actuality, as of today, we could find the roots using a numerical method. Bonus points in Taylor's heart. Does anyone know of a numerical method that finds roots of a polynomial? Adne? It's Newton's method. Yeah, absolutely. The name of my dog, because I'm a nerd. Newton's method. Very good. There are some more advanced methods, but Newton's method is kind of one of the first ones that you learn about. Okay? But Newton's method is an iterative method. And so it slowly iterates closer and closer and closer to the solution or to the roots. But it is always an approximation. It is not an exact method. And it requires this iterating, which is what a computer is really good for and is not what humans are super great at. Okay? All right, so today we're going to learn about a method to test for stability without finding the roots. So there is a method to test for stability without finding or computing the roots of the denominator. And it's called the Routh-Hurwitz criterion. Routh-Hurwitz. All right. Still seeing some feverish writing, so I'll pause. Okay, the Routh-Hurwitz criterion has 2 steps. The first is we need to generate this table that Routh defined based on some rules about how this table works. And then we need to inspect that table for certain properties. And if that table has certain properties, we will be able to tell whether the system is stable or unstable. Right? So the first step is generating that Routh table. So we're going to consider a closed loop transfer function in its kind of general form, and we'll go up to, let's say, 4th order. All right? So let's say this thing has some numerator, but we know that the poles are what really matter. So I'm not going to worry too much about what is in the numerator. We'll just call it n. Some n of s in the numerator. I really care about what's in the denominator. So in the denominator, we'll say we have some coefficient a4 times s to the 4th plus a cubed s cubed plus a2 s squared plus a1 s plus a0. Okay. Here's what our Routh table of this transfer function would look like. So in the Routh table, I give myself one row for each power of s. We call this the S2, S1, S0. And the first 2 rows, I basically read off of my denominator here. So I take the very highest order coefficient and I put it in the very top left. And then you can either put the coefficients, every other coefficient going down the row here, or you can do this. You go A4, A3 below it, A2, A1, A0, 0. And the number of columns, so if we call this column 1, column 2, column 3, the number of columns is always 1 less than the power of your polynomial. So this is up to the power of 4, so I have 3 columns. All right, every row after that is a little bit more contrived. So let's do the 3rd row here on S2. This is going to be the negative determinant of this column, A4, A3, and this column, A2, A1, all over this value A3. As I go down the row, in fact, sorry, we'll call this value B1. As I go down the row, I still have a negative determinant. The first column is still going to be A4, A3. And the denominator is still going to be A3. And in fact, we can go ahead and do that for the last column too. A4, A3, A3, we'll call this B2, we'll call this B3. However, the right-hand column of the determinant is going to be defined by what's up above and to the right. So here it was this one, here it's this one. A0, 0. And now for this very last one, I don't have anything to the right, so we assume 0, 0. We'll go ahead and fill out the rest of this Routh table, and then we'll do an example where I show you what it means to do the determinant. Maybe. Okay, so S1, I now do the determinant where I use these as the left-hand column, so A3, B1, and what's up and to the right is A1, B2. all over B1. A3 B1 over B1. 3B1 over B1. We'll call this C1, C2, C3. Okay, and then up and to the right for this one would be 0, B3. Wait a second. Nope. Hold on, something's not right. Ah. Yep, I didn't go over far enough. It's 0, 0. It's this column. Because you'll find out that B3 equals 0 when you have 2 zeros in the column. Okay, this one is also going to be 0, 0. Ooh, I'm running out of room. Here we go. B1, C1, all over C1. We'll call this D1. Minus B1, C1, 0, 0 over C1. This is going to be 0. All right, let me clean up my circles. All right, we fill out this Ruth table. Step 2 is to interpret the Ruth table. So here are the rules for looking at that Ruth table. We'll say that the system is stable if there are no sign changes in the first column. No sign changes in the first column. Furthermore, the number of roots in the right half plane, so the number of unstable roots, is equal to the number of sign changes in the first column. Okay. Yep, Martin.
Both those things have to be true? For this-
Both of those things are true. So if you look at it and you say there is a sign change, you know that at least one pole is in the right half plane, right? But furthermore, the number of sign changes tells you how many poles are in the right half plane.
Oh,
There are some special cases that you should know of. So it is possible that there is a 0, but it only appears in the first column of a row. And 2, you could also see an entire row of zeros. And if the entire row is zeros, it means that there are purely imaginary roots. okay? So here's where I'm going to get a little bit hand wavy. I'm not going to go into exactly how you handle these special cases in terms of computing the rest of the Ruth table, mostly because, like I said, I think the Ruth table is a bit outdated. If it were me, I would never use a Ruth table to try to figure out the stability of my system. I would use MATLAB. Okay, so what I think you should know is how to fill out the Ruth table for a system that is not one of these special cases. Okay, and understand the rules for the most basic Ruth table, which is you're looking for the sign changes in the first column. That's what I would like for you to take away from today. Okay, at least for the transfer function part. All right. I'm actually going to not do an example of building the Ruth array because I would rather focus on state space and then showing you how we do these things with MATLAB instead of with a Ruth array. Okay? All right, so let's move on to the state space perspective. Tell me, what is the state space form?
X dot is equal to ax plus bu and y is equal to c x plus d.
Okay, let's hear from someone not Alex. You got it right. So is anyone else listening?
Yeah. X dot is equal to ax plus plus bu.
Yep.
Y.
Very good. Thanks, Ronald. Y equals cx plus du. Very good. I totally expect you to know this. I've told you this is the one thing that I want you to know 5 years from now. Gonna keep hammering it on your head for the rest of this class. X dot equals ax plus bu, y equals cx plus du. Okay. Fun little thing about the state space is that the values of the system's poles are the same as the eigenvalues of the A matrix. As such, the system is stable if the eigenvalues have what?
Negative values,
Negative what parts? Real parts. Yep, remember these are complex numbers, so they have a real part and an imaginary part, and it's the real part that tells us about the stability.
so if we're only looking at the A matrix, isn't that independent of the forcing function?
I was hoping you wouldn't ask me that. Yes, actually, I need to clarify why that's the case. It should depend on the forcing function too, I feel like.
So it's looking at the stability of the natural system then without the forcing function?
I think that's correct.
Okay.
Yep. I think we're only looking here at the stability of the open loop system, not the forced system. But I need to clarify that and get back to you.
Okay.
Yep. If the eigenvalues have all negative real parts. Okay. Just as a reminder, if it's been a while, as it was for me, since you solved for eigenvalues, we solve for eigenvalues by finding the S values that make this true. We find the determinant of S I minus A equals to 0. Remind me, what does this big I mean? That's the identity matrix. So the identity matrix is any matrix that has ones on the diagonal and zeros elsewhere. It can be any size. It can be 1 by 1, in case it's just a 1. It could be a 2 by 2, where it's 1, 0, 0, 1. It could be 3, 4, 5, whatever it is. Okay? All right, so let's do an example for state space. So let's look at this system here and decide whether it is stable or unstable. So here we have a nice state space form. We have x dot equals a, x plus b, u, and a cx plus d, which is, I'm assuming, 0 times u. So I need to determine the s values that cause this to be true. Si minus a equals to 0. All right, so I need to find the determinant of S times an identity matrix that's the same size as A. So instead of 1s on the diagonal, I've multiplied by an S, so I'll have S's on the diagonal, minus my A matrix, close parentheses, equal to 0. Determinant of S minus 0, 0 minus 3, 0 minus 2, and S minus 8. Okay, I can simplify that a little bit. Minus 0 is just that. 0 minus 3 is negative 3. 0 minus 2 is negative 2. And then S minus 8. How do we do the determinant of a matrix? Anyone remember? It's the crisscross and then subtract thing. Yes? So I say it's the forward diagonals minus the backwards diagonals. So I take this times this, the forward, minus this times this. Forwards minus backwards. I don't want to do a 9 by 9 determinant. Yes. Again, it is still probably unlikely that you will ever be doing this by hand because MATLAB has a beautiful function called eig that will find the eigenvalues of any matrix. Okay.
Take numerical methods.
Unless you take numerical methods, in which case you'll have to learn fun things for finding eigenvalues. Yep.
Can you scroll back up to the state phase form? Thank you.
Yep, absolutely. Okay. Down here, I'll say this is S times S minus 8. Forward minus backwards equals 0. So I should have S squared minus 8S. This becomes positive 6 and then becomes negative again, equals 0. I'm still left with a polynomial that I need to find the roots of. Right? So this is where we use MATLAB again.
Is that the characteristic equation?
Yeah. So S equals negative B plus or minus square root B squared minus 4AC all over 2A should give us 4 plus or minus the square root of 64 plus 24, which is 88 over 2. Tell me about it. What happens here? How do you know? Right, so if I take a positive number and I add a positive number to it, I'm going to get a positive number, so a positive real root. It turns out the other one gives you a negative number, so you'll have one positive root and one negative root. But having just the one positive root is enough to make you unstable. So one positive real root, this thing is unstable. All right. Let's fire up the old MATLAB. Okay. All right. So let's do this for this problem that we just did. If I have an if I have an A matrix that is the same as the problem we just did, sweet, 0, 3 in the top row, 2, 8 in the bottom row. If I just say IG of A, we automatically see I have one negative root, one positive root. And you can go through with your calculator and calculate that this is indeed, this 8.69 is 4 plus root 88 over 2. Okay, so the 2 lines of code did all of that root finding for us. Now, what if we're not in state space form and we don't have a matrix? What if we instead have a polynomial? Let's say our polynomial is this other problem we wanted to do. Let's say we have a polynomial with the coefficients p equals 1s cubed plus 3s squared plus 2s plus 3. Turns out we have a really helpful function in MATLAB called roots. Roots finds the polynomial roots, computes the roots of the polynomial whose coefficients are the elements of the vector c. If c has n plus 1 components, the polynomial is c1 all the way down to cn. So exactly what I just did here, pulling out the coefficients from the highest power down to the lowest power. I should be able to say roots p and find the roots there. Okay, these roots, do they tell me whether this thing is stable or unstable?
Yeah.
What is it?
Stable.
It is stable. Why?
They're all negative.
They have all negative real parts. Some of them have positive imaginary parts, but these all have negative real parts. So it is indeed stable, but there are some oscillatory terms, so there are some imaginary roots. So this thing is going to oscillate, but is going to attenuate over time. Okay? All right, that's all I'm going to say for today. If you don't have any more questions, I'll be around if you have questions. I know that homework 2 was a little tricky in some spots, so if you have questions on homework 2, I'm happy to answer those. Yeah, so now you learned some classical history, and you learned the new age computer way to do it. Thanks all. Yep, Ronald. 10-2, we have a quiz, and 10-2, we have homework 3. So I'll be posting homework 3 as soon as I get back to my office right now. Yes. And that homework will be on the time responsive systems. Martin, did you have a question? No. Okay, good. See Noah. Yeah, you can grab it. Andrew B, got you. Is Tafari here today? Yeah, I'm here. Okay, thanks, Tafari. Okay, whatever. Leland. Is Dimitri here? No. Hey. What's up?
I didn't have time to finish the homework that was due today this morning. And I thought, workload this week crazy. I know that you can't get credit for late work, but can I turn it in at 2 p.m.? I would usually ask for an extension, but I didn't think to do that.
What is the due date on Canvas? What is the due time on Canvas? 10 a.m. Oh, I corrected it. Ooh.
If I can't, that's fine. I just wanted to ask.
Is there any? Do you have like a university valid excuse?
Yeah.
Yeah.
Oh yes.
Then
Well, no, not like absence, but like that. But it's supposed to be before the due date. I thought it was 9:59, but I'm bad at like timing that.
Okay, can you turn it in by noon?
Oh yes.
Do it.
Okay, thanks.
Yep.
Baby stapler.
What's up?
I have to be revision. Like I got the physical book, so it's like one edition before. So the questions, I just realized in the morning that I did the wrong questions. Like the questions are different.
Right, but I put the questions in the homework
I saw it
assignment.
in the morning. Can I submit it later today?
No.
Just attendance.
Ah, Natalia Figueroa. I got you. Thank you. Yep. Noah? Yes. Got you. Yep. Rhonda. Two things. Yes, ma'am. Taylor.
Attendance, yeah.
Gotcha. Carla. I got you, Carla. Amir. Thank you, Amir. Jerry.
I probably won't be at the meeting later today because I have some homework I gotta finish.
Okay. All right. Thanks for letting me know. Alan Garcia. Yeah, I got you. Thanks.
The quiz is gonna be like on the homework that's due next class, or is it gonna be like everything from last quiz moving forward?
The quizzes are more like notes content.
Yeah, I know, but is it gonna be like what chapters exactly?
I haven't written it yet. Let me see what was done in previous years. Sorry, Rhonda.
No, you're totally fine. I'm still waking up.
Looks like it's gonna be on.
I like the first one. Yeah, it's when you get on your phone too, it just looks like it's like.
It will not include today's material.
One include today's, but everything before.
Everything prior to today.
But after quiz one, right?
Yes. Okay. You can turn it in.
I'm gonna turn it in.
Oh,
but
okay.
I'm just letting you know I did not know how to do this whatsoever. I did write down this.
Why didn't you come to office hours?
Because your office hours yesterday, I didn't get out until like basically like 5, and I know you like probably want to go home, so like.
But you know that you can always ask for extra office hours at a more convenient time.
Okay. Okay, I will.
Okay.
Next time.
Okay. Thanks, Rhonda.
I'll see you later.
Yep. Hey. Yep, I just got you. Yeah, thanks, Mark. Hey.
I have homework questions.
Okay.
Well, I guess my main first question that really caused like the majority of my struggles last night was I'm not really sure how to